In this video, excuse me, we're going to talk about orbital motion, which is the intersection between gravity and circular motion. So orbital motion is essentially circular motion that is not happening on Earth, right? So we know from Earth science and just science classes in general that our solar system looks something like this, right? And the planets make elliptical orbits around the sun. And some of those planets, let me make the Earth a little bit smaller, like the Earth, even have moons that orbit them in elliptical paths. Now, like I said, these are actually ellipses, but we are going to pretend that they are perfectly circular because that makes our math a little bit easier, because when we are moving in a perfectly circular orbit, we are moving with a constant radius, which keeps a lot of other things constant. So we are taking some liberties with what's actually happening. But as we've said before, we have to start with the simplest model before we can kind of add to that. So the simplest model for orbital motion is if all of the planets are actually orbiting in a circle. So our first question is, why do planets, satellites, moons, solar systems, basically anything in space, why do they orbit? And hopefully you know by now in our kind of foray into science that all of these things orbit because of the force of gravity, right? So all of these things are orbiting because of the force of gravity. So let's take like the Earth and the moon. So we're orbiting in a nice circle, right? So the moon feels a force of gravity, right, from the Earth on the moon. And the first question we might have is, well, if that's the only force acting on the moon, why doesn't it just like smash into the Earth, right? And then, unfortunately, we probably cease to exist because the moon's pretty big. Well, the reason why is because when our solar system was forming, this moon had some initial velocity. It had some velocity tangent to the circle, right? Tangent to that circular path. And it's because of that tangential velocity that this force doesn't cause us to accelerate and smack into the Earth, but rather causes us to accelerate in a circle. Because remember, when we have a net force perpendicular to our velocity, that means we're moving in a circle. So that's why these objects aren't like smashing into us, why we don't, smash into the sun, etc. Because we have this initial tangential velocity. And when we get into rotational motion, we'll talk about why we have these tangential velocities. It has to do with a thing called conservation of angular momentum. Okay. So we have a force of gravity from the Earth on the moon. And remember, there is also a force of gravity from the moon on the Earth, right? And because these are forces in between two objects, those two forces of gravity are third law pairs, right? Which means that they are equal, and we can kind of mathematically prove that to ourselves real quick, because if we were going to calculate the force of gravity, no matter what object we were calculating the force of gravity on, this would be our equation, right? G, mass moon, mass Earth over R squared. And none of these things are going to change whether we're calculating force of gravity of the moon on the Earth or force of gravity of the Earth on the moon. So those are third law pairs. Right? And remember, the R is the distance between centers, right? So it's not the radius of the Earth, it's not the radius of the moon, but rather this distance here, right? The distance between the centers. We talked a lot about that when we talked about force of gravity. So, for a satellite or a moon or anything that is doing orbiting, right? The net force acting on that is the force of gravity. And that net force is causing us to move in a circle, so we can say that that net force is a centripetal force. So I'm dealing with orbits, right? I don't want to use Fg equals mg, or the little fg equation, because I don't know the acceleration or gravitational field that the moon is in right now. So we're going to use the big Fg equation, mass Earth, mass moon, over r squared. And since I'm focusing on the acceleration of the moon, this mass here is the mass of the moon, because I'm using my system. My system is the moon. And remember, when we're doing a net force equation, it's the mass of the system times the acceleration. My system here would be just the moon. Okay. So times AC. So what ends up happening is the mass of the moon ends up canceling out. And I get GM, or r squared, or m is the mass of the Earth, and that is my centripetal acceleration. This should look kind of familiar to us because that is also gravitational field strength. So my centripetal acceleration of any moon, planet, satellite, whatever, also the gravitational field strength or acceleration due to gravity. Okay. Now, you might be wondering, why doesn't the moon or the Earth orbit the moon? Okay. And this is actually the same question as, why do we accelerate down to the Earth? Why doesn't the Earth accelerate up to us? Right? And that's because the mass of the Earth is much, 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 much bigger than the mass of the moon. So even though the forces of gravity are the same, essentially the net forces are the same, if the mass of the Earth is very, very big compared to the mass of the moon is going to have much bigger acceleration than the Earth. And the Earth has such a big mass that its acceleration is approximately 0 compared to the acceleration of the moon. So that is why the moon orbits the Earth and not the other way around, right? It's why little things orbit big things and not big things orbiting little. Okay? Now, there do exist some instances where we have two things orbiting each other, right? Like if we have Pluto has a moon called Charon, which is approximately its same size. And these two objects actually orbit each other around some central point because they are approximately the same size. So since they're approximately the same size, they experience approximately the same acceleration due to centripetal acceleration rather, and acceleration due to gravity. And they end up kind of orbiting each other in this kind of cool little dance. So that was just a little bit of an aside, but that's how we could find the centripetal acceleration or gravitational field. Now remember, we know from all circular motion that centripetal acceleration is v squared over r. So here, this v is going to be the tangential velocity. Tangential meaning the velocity is directed tangent to the circle, but that's also sometimes called the orbital speed, right? Or how fast we have to go to stay in orbit. And then remember, r is the distance between centers. This r and this r are the same r, right? Because the radius of the circle is going to be the distance between centers, right? Or the radius of the orbit. So what that means is we can simplify, this r can cancel with one of the r's here. So this simplifies to g me over r is v squared. So if I want to find the orbital speed, that's not how you spell orbit. Orbit. You would do the square root of big G, mass of the Earth, over r. And I could figure out how fast the moon is moving in its orbit. If the velocity of the orbit changes, then my r has to change because this g and this m are constant. Right? Like the mass of the Earth isn't going to magically change, and g can't change. It's a universal, meaning everywhere, gravitational constant. So if somehow the moon were to slow down, or speed up or something like that, maybe it got hit by a really big asteroid, then this radius of orbit would change. So this is actually how satellites, etc., fall out of orbit, right? Their orbital speed changes, which then causes the orbital radius to change, and sometimes the speed changes enough such that they get completely knocked out of orbit and end up falling back towards Earth, right? That usually happens because they get hit by some space junk or an incoming asteroid or meteorite, and that's how, things can kind of fall out of orbit, so to speak. So that's our orbital speed. Okay? Again, nothing here is really too new. We're just applying the force of gravity to circular motion. Okay? Now, sometimes what can also be really useful to find is the period of orbit. Okay? This especially comes into play when we want something called a geosynchronous, I don't know if that's spelled right, definitely not an H, geosynchronous satellite. Okay? I'm really bad at spelling today. So geosynchronous satellites are really cool because they stay above the same exact spot on Earth as they orbit. So,
please submit your attendance at this time. Thank you.
Sorry, guys. So they stay above a specific location on Earth. So what this means is they have to rotate or, complete a circle in the same amount of time that the Earth completes a circle. So they need to have an orbital period the same as the Earth. And hopefully we all know that the Earth orbits itself or revolves around its own axis in about 24 hours. So if we know that we need our orbital speed to be about 24 hours, we know that there has to be probably some specific radius and some specific speed that it has to be at. Right? We could also have an orbital period of maybe we want it to pass the place once every 2 days. So that would mean an orbital period of 48 hours, etc. So what scientists do is they take this v-orbit equation that we just came up with, GME over R, and they say, okay, well, this speed here is really the speed of something moving in a circle, which is equal to that circumference over the period. GME over R, right? And then they solve for this period, because if we need this period to be something specific, right, we need the rest of it to match up. So in order to solve for t, I'm going to flip both sides. So t over 2 pi r is the square root of r over GME. That's a fun math trick you can do. And then I'm going to multiply by 2 pi r. So my orbital period is 2 pi r square root of r over GME. Okay? Now remember, no matter the satellite, big G and the mass of the Earth is going to be the same. Okay? So if I need my orbital period to be 24 hours, then this r has to be a very specific number. So what this means is that all of our geosynchronous orbits are at the same, oh no, I'm having a lot of issues today, are at the same radius. And actually this, if you've ever looked at a picture of all the satellites orbiting space, there's just like a bunch of satellites in like this one specific orbital radius. And those are all of our geosynchronous satellites. It's kind of like this weird ring of satellites around the Earth. Because if we need our geosynchronous, right, 24-hour period satellites, they have to be at one specific radius, right? So it can get kind of messy up there. And it takes a lot of planning to launch those satellites because we've got to make sure they're going into an open spot and not knocking another satellite out of orbit, because satellites are very expensive, right? So this also tells me that if my radius changes, the period is going to change as well. So if I need, like I said, a 48-hour orbital period, I have to go at some distant different radius. Okay. Now, the relationship between period and radius is quasi not important as my screen goes black again. Where'd it go? Hello? Okay. Oh my goodness. I don't know what's happening. Computer isn't even connected to anything. Okay. The relationship between period and radius is a little bit funky. It ends up being, because this R can go back under the radical. Oh no. Now my pen is okay. It ends up being a T is proportional to the square root of R cubed. Like I said, not really important in the grand scheme of things. But yeah, so just to recap this video that got off track very quickly. Things orbit because of the force of gravity. Two objects that are orbiting each other experience the same force of gravity, but the smaller object does the orbiting because its mass is usually much less than the other, right? Unless you're in the case of like Pluto and Charon, where we have two objects of similar mass orbiting each other. So because of this, the force of gravity becomes the centripetal force. We can use that force of gravity to calculate the centripetal acceleration, which we showed was the same as the gravitational field. Okay, we then calculated the orbital speed, right, which ended up for the moon being g mass Earth over r. We could replace the mass of the Earth with any mass, like say we're trying to figure out the orbit of one of Jupiter's moons, we could replace that m with the mass of Jupiter and the r with however far the orbit is for those moons. Then using that orbital speed equation, we can find the period of orbit or the time it takes to go around. This is really important with geosynchronous satellites, which we need to have a specific orbit of about 24 hours. And that is the end of orbital motion. I have no idea what this video is going to look like. Hopefully it makes sense. Okay, bye.